Perfect. Perfect. Okay, we're gonna get started with our workshop. It's gonna be Intro to AI/Machine Learning. So this is also gonna be a live stream. So if you want to check back it later tonight, you definitely can. It'll be on our YouTube channel. And to introduce you guys, this is Sean. He's one of our mentors, and he's actually a UTSA alumni. He just graduated recently. So, definitely if you want to learn more, hit him up as a mentor. And let me pass it over.
All right, man. It's still crazy to be here. This is my second time in the mentor capacity. This is actually the 4th Rowdy Hacks I've attended. It's so great to see so many people be engaged in this kind of activity. So actually, before we begin, I just want to very quickly run through my conference speaker mode. I want to first thank the ACM chapter, our ACM chapter here at UTSA, for putting on this event. All the amazing organizers here. Some of them are like dear friends. Some of them are my former students. Amazing people. So whenever you see an organizer, just anytime through this weekend, just thank them. They worked countless hours to put on such an amazing 10th installment of this event, and I am ever grateful to them. And I also I just want to thank them for having me host this workshop. So you probably see from the title slide here, and you'll probably see, well, that looks like a funny looking PowerPoint. It's not PowerPoint. So you'll see from the title slide here, this is a mathematician's guide to machine learning. What does math have to do with machine learning? Well, a lot. So we're going to go through some mathematical foundations. I won't assume too much, because then we'll be here talking about covariant and contravariant tensors, tangent spaces, and bundles and everything. I don't want us to get into that. But you'll get some foundations of where the math plays in, why it's important, and then how you can use that when you scale it to your own AI framework and everything. So let's just kind of start off with who I am. That is a silly picture of me. So who I am, I'm a mathematician by I guess you could say by study, an operations researcher by trade, and also a former musician. I was in an internet ska band in the spring of 2020. We can talk about that later. Played music in high school and everything. I got my undergrad at A&M San Antonio in 2015, and then very shortly after, I moved to College Station to attempt a master's degree at Texas A&M. For reasons that didn't work out, I moved back here, and I got my master's degree in applied industrial mathematics here at the University of San Antonio in May 2024. So yes, I have just graduated, and let me tell you, it is real. Finished grad school after a long time, and to really see that success. So that's just a bit about me. I am a mathematician by trade, and I really have gotten into data science very recently, within the last 3 years. Mainly before, my interests were in combinatorial optimization, so graphs, networks, and everything. Then I kind of transitioned to doing a lot more scientific computing. Right now, I'm helping with a project implementing a neural network to solve certain fluid flow equations to simulate the flow of fluids in a vacuum. This is a NASA-funded project with my research advisor, Dr. Vu Hong, and a couple of my other classmates, Gavin Cunningham and Dave Cantu. So just a bit about me. And I've had a lot of experiences through this. So if you know me or know anyone that's taken Calculus 2 in the last year and a half, you may have recognized this slide from the trigonometric integration video. So I was a TA for Calculus 2, and I have made a lot of work there. So, a lot of people have come up to me in the last year on and off just saying, hey, your videos have helped so much, thank you. So that's a lot of what I did, just a lot of calculus stuff. I also competed in the very first 2 Rowdy Datathons in 2022 and 2023. My team won the very first one with our project. And I also mentored at the previous one we had a few weeks ago. I also competed in the 8th edition of Rowdy Hacks. Our project was called, what was it called? C2C. Yeah, C2C. I got to put that on my website as well. And I've been basically retired from competitive hacking, if you call it that. I've been mentoring at a lot of different events, mentoring at this one, mentoring at Rowdy Hacks 9, 8, 9 and 10. Mentored at the last Rowdy Datathon. Mentored at Code Quantum Hack Day. Code Quantum is, I believe, coming back again in the spring. Okay, I got the okay from Trey. And the two people that are the directors, again, two of my former students, Ikra and Anusha, just amazing folks. More info on that. But really, I've been doing a lot of math and teaching, but I've now transitioned to doing operations research. So for those that don't know what operations research is, it's the blend of mathematics and statistics and optimization to solve like these big decision problems like you may see in like the business or corporate world or government world. Like for example, one problem that I'm working on right now is at work is, for example, how many pilots do we need to train at Randolph Air Force Base so that when we transition to a brand new syllabus for a brand new kind of jet, we have enough instructors to meet that demand. Sounds simple, but it's actually not. It's more like an inventory logistics problem. Weird optimization things there. All right, so I want us to like really think about machine learning for a second. So let's just, this is me going back into teacher mode. I taught high school for a while as well, so we're gonna be a little interactive here for a second. So when you think of the phrase machine learning, okay, when you think of the phrase machine learning, okay, what words come into mind? Okay, yes? Large data sets, okay, anybody else? Yes? Say that again? One more time? Tensors, vectors, oh yes, the dreaded T word. Ugh. You know, finding a contravariant basis for a tangent space on some manifold, anyway. What else do you think about like with machine learning, or even artificial intelligence, AI? What else? Yes? Skynet, okay. Kind of fits with the 80s theme of this, this hackathon, you know. Anybody else? Yes? I thought of chess engines, okay. Yeah, yeah, Torch, yeah. Are you an E4 or D4 player? Ruy Lopez, why? I'm a guy to play, this guy to play in the Italian. Okay, so chess engines, okay. Stockfish, yes sir. Who else had one? Yes. Chatbots, yes, very good, chatbots. That's been in the zeitgeist. I can take like one or two more. What else do you think of with AI and machine learning? Yes, sir. Linear algebra, okay, yeah, now you're really getting to me there. Oh man, love it. So, all those things, right? So there are some mathematical frameworks, but we also see this in the zeitgeist. Right? Large language models have taken off over the last 2-3 years. You know, OpenAI has their thing. Microsoft Copilot, Llama, Claude, Gemini, formerly called Bard, right? Grok with a K. Yeah. But what really is it at its source? Like, we really hear about it, but what is it? So I just kind of pulled some things from a couple of sources. There's a book that I really liked using when I took a class last spring, actually, one of my last classes here at UTSA. Mathematics for Machine Learning. It's this text by Dyson Roth and other authors. I believe that one is available for free. I think it is. So they describe machine learning is about designing algorithms that automatically extract valuable information from data. Okay. Oh, the stream is looking kind of weird. Oops. Okay, well, we can tidy that up. Okay, so we're getting information from data. Now, from IBM's site, machine learning is a branch of computer science that focuses on the use of data and algorithms to enable AI to imitate the way that humans learn. ML is how computers learn from past experiences. It's how we learn from what we've seen before, and then we learn on new things. Like, for example, yeah, kind of like that. So, many ways that you can think about this. All right, let's play a game. Chihuahua or muffin? Chihuahua or muffin? The first one is a muffin in the 1-1 entry. Okay. Chihuahua or muffin? Okay, so why do I have this funny slide up, right? So this is an example of what could be a basic machine learning task, classification. Is it a chihuahua or is it a muffin? Right? Some of these look very similar, but you probably know, like, blueberry muffins have certain features, right? Chihuahuas have certain features. Okay, that's an F word that we're going to use now, not the other one. Okay. The joke I used to tell, like when I used to TA for calculus, band-aiding algebra stuff, people would like look at multiplying polynomials and like, yeah, use the F word. They look at me funny. I'm like, not that one. The four-letter F word, as I would call it, because it basically is about, we're like, you don't think about multiplying polynomials by just FOIL, because it only works in 2 by 2. Anyway, Chihuahua or muffin is an example of a classification task. You're given these images, and you just want to say, tell me if this is a picture of a Chihuahua that I can pet or a muffin that I can eat. Okay? Now, if you mix those up, that would be pretty bad, right? So this is just an example. It's a funny example, one of the meme ones that probably circulated over the last couple of years, but it gets the point across. So what do I want us to get out of this talk, okay? So I really want to have us understand the basic mathematical framework of machine learning. Okay, yes, there's math involved, okay? But I'm gonna make it less scary, I promise, okay? That's how I got a lot of people through calculus, okay? We're gonna look at some basic supervised and unsupervised learning tasks, okay? Those are the two classes of machine learning tasks that are out there, supervised and unsupervised. And then we're gonna experiment with some data sets in a demo. Okay, so pretty simple. Me talking part shouldn't take too long. We'll probably have like a little interval in the middle to like get your environment set up, and then we can look at the actual demo. Okay, so we're gonna start with the mathematical framework. So let's just kind of do a bit of a poll here in the room. How many of you have taken or are taking calculus in some capacity right now? Jolly good. Okay, everyone's hand should be up. Linear algebra. Okay, so the word basis and eigenvector, and yeah, those should be familiar words. Okay, linear transformation. Okay, how many of you have taken like any statistics class, be it in high school or in college? Okay, very good. A course dedicated to just probability theory, like just probability theory. Ah, okay. Discrete math, let's just think about that. Discrete math, okay. All of our CS students should be taking it now. Combinatorics, how many of you have heard of combinatorics? Okay. Graph theory. Okay. So there's these different branches of mathematics that all come in to think about this awesome computer science thing that we usually associate with computer science. There's a lot going on behind the scenes. I really want to give you guys some of those basic foundations, okay? All right, so what's needed? So there's a lot that we could really talk about, okay? If you've read any machine learning paper or documentation, which by the way, keep up on the latest research, like look at preprints on arXiv and the like, some of them you can probably get through the abstract, but understand, like looking at current literature is how you stay current as a student, especially as a graduate student, if you go through that route as a master's or PhD student. So we're gonna assume that we all know how to do derivatives, so differential calculus. We know how to do dy by dx, okay? We can do basic optimization tasks, take the derivative, set it equal to 0, find the critical points, and then use the second derivative test if you need to, okay? Basic probability, like very, very basic. That's it. Not expecting everyone to know like n choose k type things or Gaussian kernels, just very basic probability concepts. And Python, or your language of choice, but it's all basically done in Python these days. You can implement this in whatever language you want. Like if you want to do this in C, I mean, God help you, but you can. I mean, C is fast. I'll give it that. C is a fast language. I just haven't really had much use for using C or C++. Okay. Now, other things like linear algebra, I won't really assume here, but I will mention some like matrix computations, but like we're not really gonna use a lot of linear algebra here. Okay, if you do wanna learn linear algebra, there are like lots of great references there. For example, the MIT course, OpenCourseware 1806, taught by the legendary Gilbert Strang. His lecture videos are up there. And other advanced topics which you could really get into, like topology, like topological data analysis, numerical analysis for like understanding if like your algorithm actually produces a reasonable approximation to your optimization problem. Functional analysis, just some other nonsense. We're not going to, we'll brush that out. But if you want to talk to me about it, hey, I can fake my way through it. So what is the objective? Well, it's an objective function, okay? So in machine learning, depending on the task you want to do, okay, like before, Chihuahua or Muffin, what do you think we want to do? We want to correctly classify the picture. So maybe we have like a true positive rate that I'm trying to maximize, or something that is seen with like these binary classification tasks is a cross entropy. But in general, okay, depending on the kind of function, the kind of task that you're doing, there is an objective function, a thing you want to maximize or a thing you want to minimize. Okay, you guys have heard of loss functions, perhaps? Loss functions in machine learning? So what a loss function is this kind of metric that measures like how good your algorithm is doing. Okay, for example, maybe the loss function is like a mean square error, if you know about regression, okay, which we'll talk about soon. But it's an objective. It's an objective. Every machine learning task, there's a word missing there, oops, starts with an objective. I want to maximize something or minimize something, like maybe mean squared error, a likelihood or log likelihood function. Cross entropy, those are common examples, okay? True positive rate, even. Your favorite machine learning library has all these loss functions and documentation about them. And want to minimize or maximize it subject to some constraints. So now we're talking about really a constrained or possibly unconstrained optimization problem. And that's where the calculus comes in, right? Maybe I have this loss function here on the left, this surface, and I want to find a minimum. Now, of course, in this example, I have infinitely many minima along a line, but it doesn't really matter. I can find that by using my favorite algorithm, gradient descent, Newton's method, stochastic gradient descent, if you ever heard of that. Or just do the Calc 1, Calc 3 way, right? Take derivatives, the gradient, set it equal to 0, do some stuff, blah, 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 But every machine learning task has this at the background. That's what's happening. There is a function that is driving what we're trying to do, and this is like a cost, and we're trying to minimize that cost. Minimize the error, maximize the true prediction rate. Okay? Now, again, I said I wouldn't really get into math, but like there's some really basic things here. So elementary calculus gives us necessary conditions for minima. Now, what is a necessary condition? It just means if you have a minimum, then you know some extra things about it. Okay? So this is like in the Calc 3 context. So if I have a minimum at some point, let's call that point X star, maybe, because is a star point where everything just happens nicely, okay? But if you have a minimum, what do you know? There's no change. The derivative is 0. The gradient is 0, okay? If you don't know calculus 3, that little upside-down triangle, that's the nabla, where we use for the gradient vector, because now we're talking about several variables, and by several, I may mean like hundreds, nay, thousands of variables. So these optimization problems can get huge when you scale up. They can be really big. So it's important to understand what happens at the small scale. Okay, those toy problems you may have done in Calc 1 and in Calc 3, and a specialized class for optimization. Understand what happens at the small scale so that when you implement something, you can kind of have an idea what's going on. But as we may know, isn't enough to say that if my gradient is 0, do I have a max or min at that point? Do we remember that from Calc 1 or Calc 3, right? If I have the derivative equal to 0 at some point, do I have for sure have a max or min? What do you sit on when you ride a horse? Saddle points. We want to avoid that. So this is necessary but not sufficient. It's not enough. You have to avoid points of inflection in the one-dimensional case, or in several variables, these saddle points. Like if you look at a little single Pringle chip, right? How it looks like a saddle? Well, you're trying to avoid that because you don't know if you actually do have a max or min there. So you got to have a bit of extra work, a bit of extra tools. Okay, so you have this extra condition, okay? You have to have the first derivative be 0, but the second derivative be positive. ways to generalize this in several variables. We'll skip over that, but the big thing here is this last line here. Remember from calculus, right? Take the derivative, set it equal to 0. You have one problem of finding these minima, but the extra problem is when you set the derivative equal to 0, you're also doing a root finding task. You know, in algebra, we solve equations, right? We know how to do it. Like move this stuff over, or factor, that's the other F word, or take logs, or whatever. Can you actually solve by hand any single equation that you put down? No. So you got to resort to different numerical methods. Newton's method, bisection, autogradient-based methods of sort of line search. So now the hard part now is not just finding the minimum, but also solving this problem. So now your algorithm has a bunch of other steps to go through. Finding the zeros of this derivative, you have to do this numerically. And then there are libraries that can do that very quickly. LAPACK is the library of tools that's been around since like the 70s. Since anybody know about Fortran? Fortran, the programming languages. It's old. It's old, baby. Those packages have been around since the 70s and been ported to like every language known to man and several known to monkeys. That's a joke. And those are optimized to really do the job. So if you know about MATLAB, anybody use MATLAB in here? MATLAB, Matrix Laboratory. Not a sponsor by MathWorks. MATLAB has efficient routines to solve these equations and like solve these optimization problems, especially in their optimization toolbox. SciPy.optimize in Python has routines for that, but they're just ported over from the old routines. So what am I saying? It may sound easy to find minima, but the instant you solve this equation, this f prime of x equals 0, or if you have several variables, you have n variables, grad f equals 0, you're solving a system of nonlinear equations. That is hard. And now you got to pick another tool to do that job. So you're going to learn that with machine learning, yeah, you can like frame out what you want your thing to do, but also you need to think about what happens along the way. Do I need to do a bunch of matrix multiplications? Do I need to invert a matrix? Please don't invert matrices, guys. No, just don't do it. Do I need to do some factoring? Do I need to solve successive constrained optimization problems? And that's what happens in the background of these machine learning tasks, especially when we scale up to like large language models, generative text, generative images, okay, and even music and the like. So there's a lot of minimization algorithms. I probably mentioned a few. You may have heard of gradient descent. Gradient descent, people have heard of that? Yeah, gradient descent, that's like one of the classical root finding algorithms. So what is gradient descent, okay? So let's flip it to gradient ascent, okay? Gradient descent, you're trying to climb a mountain in the shortest amount of time. It makes sense to like go in the direction where the mountain is the steepest, right? You take one step, climb, set up camp, reassess your surroundings. Okay, I need to go this way. And then you summit the peak. That's what gradient ascent and consequently gradient descent does. We're trying to figure out the direction of fastest change so that we can get to our maximum or minimum depending on the problem, okay? Now, of course, there's an easy picture for this, okay? This is an example of what's called a contour map, where each curve is like at the same elevation. Like, have you guys seen, like, anybody do, like, hiking or mountain climbing or, like, at, like, national parks or whatever? I'm clearly not athletic, so I just, like, pass out after, like, 2 minutes. And I almost tried to do Joshua Tree this summer, but I was too lazy. Beautiful, by the way. Weekend in the high desert, amazing. Pictures on the Instagram, by the way. So this is an example of what gradient descent can do. We start somewhere, look at where we're going, where we can get the best increase or the best decrease if we're minimizing, take a step in that direction and reassess. And we keep doing that until we're satisfied. But the problem is it always easy to do this? No, it's not. We have to do a bunch of different things. Different line searches, randomized gradient descent, okay? SGD, stochastic gradient descent, Attograd, Atomax, all that. So now there's a question of which algorithm, okay? You have a class of algorithms that you can use, but You gotta find the right tool for the job, right? You don't just wanna like, take a jackhammer and just like nail something into your wall, right? Well, I mean, that would be fun, right? But you wanna find the right tool for the job that you're doing. So you have to assess the size of your data set, the size of your variable space, okay? The size of your target space even. Few ways you can think about this. Batch gradient descent. So you run through the entire data set. Then you take the gradient. This is really stable because you look at the entire data set and it's like, oh, okay, here's the gradient. But as you scale up, it gets really slow. I'm talking about like I-35 at rush hour slow. Thank you, I'll be here all night. Okay. So that's one way of doing batching it, okay? Doing this in like one batch. You can even do smaller batches if you want. Some packages allow you to like change that. Stochastic gradient descent, it's very popular. SGD, okay? Like I'm adding that to my three-letter acronym thing, like FTC and IBP. See, right? Integration by parts, favorite thing, okay? SGD is popular, like very popular. It's like a default thing in a lot of packages, okay? You update the gradient after every training example. So you run through the entire data set and you change the gradient after all of that. But the problem is, okay, you may have to tune your step sizes because you can overshoot. You can cycle back and forth and think, I found the minimum, and you haven't even looked down. That's another problem with tuning these algorithms. Adaptive gradient descent methods are also popular, like Atagrad. You change the step size progressively. So like you run through your set, and then after a certain amount of time, you maybe like take half of the initial step size and take half of that and just keep making it smaller and smaller so you don't overshoot. I like doing this, okay? But the problem is with the tuning of this, of having the step sizes, you need to make sure that you have enough computational resources. So you have a GPU, you can offset this to like a cloud platform like Colab, okay? The moral of the story is think about the model, think about the performance based on the size of your model, the size of your data set, what computational resources you have, and look at the documentation. Like if that's one thing I can tell you, like look at the documentation and see like what optimizers you can use. Okay, I hope I haven't scared anyone else yet. Okay, like I said, there is mathematics behind machine learning. It's very important that we understand at least some of the basics. I'm not saying we need to know, vector calculus and everything, or like master linear algebra. No, just get a little bit of it, and then you can learn on the fly as you go. Okay, because when you read the documentation, it's like, what does this algorithm do? They will have the mathematical formulation there. In fact, when we'll get into scikit-learn, okay, the user guide there actually does have mathematical formulations for almost every algorithm there. Okay, from every algorithm there is a mathematical formulation. So we're going to talk about supervised learning first, okay? We're going to talk about supervised learning. So what is it, okay? You have a labeled data set. So I already know that this is a chihuahua. I already know that this is a muffin, or even better, this is a bird, dog, fish, frog, cat. I know what the object is, but I want to train the model to be like, hey, tell me what this thing is. Tell me what this new thing is, okay? You want to learn the patterns, extract some of the features perhaps, and predict outcomes. So for example, a regression task predicts continuous outcomes. Again, if you've taken a stat class, you may know about linear regression, right? Okay, push the button on your calculator. Yeah, we've done that. I've done that too for years. And classification predicts a category. Okay, this is a fish. This is a plane. This is a truck. This is a tree. Okay, so think about self-driving cars. They need to think about, say, segmentating, taking segments of those of live video feeds. That can be an example of a supervised classification task. But the labels act as a teacher. You are there. You're basically giving it flashcards. Okay, think about it when you study for like bio or psych or whatever. You have flashcards, okay, for things. You look at it, look at the back, okay, all right, and then you find a new thing. I think it's this. Oh, okay. Think about this like when you also study as well, right? Again, bringing it back to the calculus. You may have seen me do lots of exercises in the videos, but you go to a different text and you see a problem you've never seen before. You attack it based on your previous knowledge because you have learned from your, say, your training set. Okay, so over here, this is a 3-class classification problem from this book, which is amazing, An Introduction to Statistical Learning with Python. It's free. They finally released a Python version of this book, which makes me happy because originally it was an R-based version of the book. You can just do a lookup for this, and you'll be able to find it. Okay, An Introduction to Statistical Learning with Python. It is a mathematical text, but it also shows you like a lot of good visuals, like how these algorithms work. So let's just look at a simple task we've probably all seen before: regression, linear regression. We're going to take the most basic form. I have a bunch of points of the plane, x comma y. Okay. I want to find a line that best represents this data set. You've probably seen this in your introductory stat class, right? Okay, probably towards the end or maybe the beginning, depending on how it's taught. We have a bunch of points. Can I find a line of this form, beta 0 plus beta 1x? I choose that instead of mx plus b because of, well, we're calling the parameter here beta. Now, best implies something. It's an objective that I want to minimize. And in particular, I want to minimize a square sum of residuals, okay? Basically, I want to take every point on that line and see the actual data point, and I want to make sure that like all those distances are as small as possible. And so we do this for like however many we have, 50, 100, 1,000, whatever. We've all done that. I'm pretty sure we've all done this task before, and it's easily solved in the computer. I need to find the slope and the intercept to minimize this function j. This is an example of an objective function. So we can actually solve this problem. I won't go through it. It's based on like the covariance and everything. But the thing is, there isn't much to learn here. There's a tidy solution. So why don't I actually just do this all the time? Because it involves inverting a matrix, and inverting matrices is terrible. It takes a lot of time. Scikit-learn actually does have ways to do this for large and probably badly behaved matrices. It has a way of doing this, okay? It is linear regression is the class that you have to import from scikit-learn. I'll show you that in a bit. And the computation of these inverses is avoided by doing different factorizations. Again, they're in your favorite linear algebra text. So you can actually use the usual train test split and some other optimizations to get a very good approximation of what the actual regression line is if you solve the so-called normal equation. So there was a question in the back. Ooh, that's a very good question. So what is a badly behaved matrix? Oh, man. So badly behaved in this sense means that the condition number, or one way of measuring if a matrix is well behaved is like looking at the so-called condition number. The condition number is the 1 over the size of the smallest eigenvalue in some texts. Basically, it says like if you change just one entry of the matrix, does everything just like blow up? So an example of such a matrix is called a Hilbert matrix. For the Hilbert matrix, you basically take the row column coordinates, add them together, and then do 1 over that. That goes in that spot. It's very badly behaved. So like if you change just one entry of that thing, like inverses blow up, you have a lot of numerical computation funkiness that happens. Maybe some of you are probably familiar with like floating point computations. You know, all these matrices are stored as floats in your language of choice. Okay, so if you're not careful, and if you have a very badly behaved matrix, you're gonna get some like really funky results, okay, if you perturb. Okay, texts in some introductory linear algebra texts talk about condition numbers, but you'll probably get a good treatment in like a numerical linear algebra text. The one kind of Bible, so to say, for numerical linear algebra is by Trefedin and Bao. I can give you that reference later. Talking about like condition numbers and like how you solve linear equations with like these very badly behaved matrices. But you know, if you have a data set whose matrix representation just looks not great from some perspective, then computing inverses is going to be very, very bad. And like you avoid that by using the SVD, which I do have a talk that I have not posted on my website yet, but SVD is a very good thing. QR, other powerful factorizations are out there. There's like a lot of machinery under the hood that scikit-learn takes care of, so you don't have to worry about it. And also, so I don't have to worry about it. Okay, so let's think about regression here. So I have a bunch of data points, a cloud of data points. Okay, my blue points, okay, are my training, is my training set, okay, what it looks at first to gather an idea of features. And then the orange points, I wonder why I chose blue and orange. Words up, baby. Orange is the test set, okay? So after we fit the model on the blue, we're going to predict with the orange. Now, what I've done here is I've actually solved the regression problem by using the normal equation, the actual linear algebra, x transpose x inverse x transpose y, do all that stuff. And I do that with this red line here. You can kind of see that. And then the green is using scikit-learn's built-in stuff. Pretty good, right? I don't have to worry about this nonsense of inverting a, oh God, this was like at least a 200 point data set. I can't remember how large this data set is, using the BMI, the diabetes data set, which is one of the ones that's built in scikit-learn. There's lots of toy data sets there, great documentation. But pretty good, right? I don't have to solve the actual equation. I can take like an iterative approach, so to say, by doing a train test split. Okay, so I can look at like say 80% of the data, and I can still get something that approximates the actual thing. Take a quick coffee break here. All right. So we now have a not so tidy problem, and that's called classification. Okay, so back to Chihuahua versus Muffin. Okay, that's image classification. Now, image classification is a bit harder anyway, but let's think about this in the plane, okay? Red versus blue. Anybody remember that series? Yeah. Who was around on the internet in like 2008? Heck yeah, there we go. Okay. Love that. So, red versus blue, okay? I have a bunch of points here. Some of them I'm going to put in class 0. That's going to be colored red. And some of them are going to be in class 1. Those are colored blue. The question, can I find a line or some other boundary type thing, depending on the kernel that you choose? Can I find a way to easily separate these two and decide best if I pick a random point on the plane, does it belong in class blue or class red? That's an example of a classification task. But why did I show this in the plane? Because when we talk about like image classification, we're kind of like projecting onto, or like casting it into some high dimensional vector space, some like Rn type thing. The word of the day is isomorphism. That's your SAT word of the day. Okay, so classification, it can be very difficult, especially like you can see, like there are some points that kind of like lie in the middle. It's like a toss-up which one they belong to. And depending on the algorithm that you choose, okay, depending on the algorithm that you can choose, okay, it tells you, like, gives a way of classifying these. So what are some classification techniques? There's logistic regression. Okay, this one is now predicting an odds ratio, so it can tell you like there's a blank % chance that this is in class A. There's a blank % chance this is in class B. Okay, it works for 2 classes. You can generalize this to multi-class. I think it's a little kind of messy, so I usually stick with the 2-class, the binary class example, like before. Support vector machines. I really like these. You're basically trying to fit a hyperplane in higher dimensions. So think a line that best separates the data, and you can allow for like some misclassification, hinge loss, and whatever. Decision trees basically ask a bunch of yes or no questions. Okay, like for example, like think about like trying to see if a dog is a German Shepherd or a, I don't know, give me another dog breed. That one. Labradoodle, sure. Okay. Well, maybe you might look at the ears, okay? Are its ears pointy? Yes or no? Is it big? Yes or no? Does the coat have this kind of feature? Yes or no? That's what a decision tree is. It asks a bunch of yes or no questions. Nearest neighbors. I like this one too. Think about nearest neighbors. It's very easily stated. Look at a point and look nearby on the same, on the same street corner, right, or the same subdivision or whatever. Can you predict its features based on that? I like nearest neighbors. Okay. You can do nearest neighbors on like a number of neighbors or like some sort of distance metric. So I visualize this here, same data, different approaches. Okay. Logistic regression on the left here. Same data set, by the way, and same training test split. But I'm doing the same algorithm. I'm using 3 different algorithms on the same data set. And you can see that some points have been misclassified differently. Some points may have been classified correctly. Some points may have been misclassified. Different points may have been misclassified across different ones. So logistic regression, do this odds ratio thing. Okay, I can kind of see that. All right. But now if we move over here to 3 nearest neighbors, what that does is it takes a point and looks at its 3 closest neighbors and predicts based on that. You can kind of see there's like a larger clump of misclassified points here versus in logistic regression here in like the bottom left. And then when we look at a stochastic gradient descent kind of classifier, it's a little funky with how it does it. But again, we have some misclassified points here as well. So you can use the same data set, look at it differently, and sometimes get wildly different results. And the big thing is you have to understand the tool for the job. How's your data set structured? What are you trying to find? What are you trying to measure? Does this algorithm make sense in this context? You can't just pull a thing off the shelf and it's just like, I'm going to do it. Well, you can, but you got to make sure that your thing makes sense. All right. And just real quickly, unsupervised learning. This is basically like learning on your own, okay? Like, how many of you have like tried to learn a new skill like by yourself just by looking at books and websites and YouTube tutorials? Oh my God. I tried to learn stochastic calculus on my own. That was not fun. I've learned programming languages on my own. It's been very not fun. But what is unsupervised learning? Now you just have the data set, no labels, you just got to figure it out. Okay, so this is like, again, finding common features across dog breeds, but not understanding what the features are. Or getting shapes and images to detect objects. Like, is this a tree? Is this a person? Is this another car? Right? Patterns in medical images. I like this. How many of you have like heard of like medical imaging and like image detection? It's been a pretty big field right now with, finding tumors and cancer patients and everything. But the thing is, we don't know what a tumor really is until we actually really see it, right? So we can like make a guess, see like in this region, there might be a tumor. Unsupervised learning is us learning on our own and trying to identify the patterns on our own. We set it and forget it. So one example is called clustering. Take a look at the picture on the left. This is the unlabeled data set. Same data set in both pictures. How many distinct groups do you see? No cheating. How many distinct groups do you see in the left picture? Maybe. How many of you see 2? I at first saw 2. How many of you think there are like 3? 4? Or maybe more. This is an example of what clustering does. You have no information on what the labels actually are. You just got to figure out what's best. So if you apply a clustering example, this is from Google for Developers, okay? We can if we want to like put this into 3 classes, this is what it comes up with based on a certain clustering algorithm. But how are you sure that this yellow point here isn't actually colored red or colored green? There's no human supervision. You're just left to your own devices to like figure it out for your own. And unsupervised learning can be hard in that regard. There's a lot more to try to figure out. Again, think about the algorithms that you want to use. Think about the task that you're trying to do, okay? And make sure that you choose the right tool for the job. Okay, and don't be afraid to do like iterative approaches, like tune these parameters or whatever. That's what the documentation is there for. All right, so where can we go from this? Okay, there's a lot more. I mentioned briefly topological data analysis. Sometimes the geometry of your data set is important. If you want to look at, say, income disparity in San Antonio, you might be able to see a difference between, like, say, outside of 1604 versus inside 1604. That's not a perfectly rectangle. It's like a donut shape, right? The geometry of your data set is important, so you can learn off that. So L-shaped, Swiss roll type things, donuts, toruses. And of course, we all know about neural networks because we hear about them in the literature, okay, deep learning. That's a subset of this stuff, where you just do a bunch of iterative training. And the way that you design these neural network architectures can determine if you're getting very close to solving your problem, or you get just like, garbage. It's an art as much as it is a science. You got to play around with it. That's what I've been doing with like my neural network solver. I have to mess with the layers, the operations I'm doing, activation functions. We may have heard about that. But it's an iterative process. Minimize, repeat, update, minimize, repeat, update. So I've given you like some of the mathematical framework here, okay? And so what are we going to do? Well, we're going to do like a little short demo. I really want you to see like how we're going to do all these things, okay? So right here is my website, szrobertson.github.io. I actually did build that with GitHub pages. And I'll actually show you in a second where to get that. Is if you scroll to the projects at the bottom and a mathematician's guide to machine learning, you'll see like my previous version of these slides that I gave. These slides, you can download them there as well. And I also have a link to a Kaggle notebook. Anybody use Kaggle before? Kaggle? If not, that's okay. And there's also a link to the actual Jupyter notebook. Okay, so in fact, I'll go ahead and go to my website here. Oh no, oops. This is scary. I'm sorry. Sorry to anyone that's watching this on stream. Okay. So yeah, I built my website. It's pretty nice. And actually, while we're here, I guess I can kind of plug this a little. If you ever want to get in touch with me, LinkedIn is right there. My LinkedIn is there. Email, you can get in touch with me if you need some career advice maybe, or if you're thinking about doing some other math stuff or CS adjacent stuff, I can definitely help with that. In the projects here, a mathematician's guide to machine learning. Okay, there's the Kaggle notebook, which if you have Kaggle, you can go ahead and click that and you'll be there. I think you may have to do a copy and edit onto your own Kaggle notebook. But if you do have Jupyter installed on your machine, you can actually download the notebook here at this last link to download the actual notebook file and put it in Jupyter or VS Code. And I'll be going around in just a bit to help some of y'all with that. So I guess this is a good chance for an interval. We'll give some people here to set up, and we'll be back in a few minutes. All right, so we got some bug fixes, to put it mildly. So let's. So if you have been able to like actually download the notebook from the website, I think we did have it fixed. But I have this now open in Jupyter, which is a notebook application, very interactive, easy to use for like a lot of teaching applications. I've written many of this for like my students and for class projects. Some of you may have as well. So I'm going to go ahead and open the notebook here in Jupyter. Some of you may have this happen open in Kaggle. If you have to log in with your account to actually like make the to actually edit the notebook, you can also copy this into. Anybody heard of Google Colab? Also, yeah, you can put it in there as well. Whatever you want to use. So this is a notebook that's just a bit of a slightly interactive demo on how some of these machine learning algorithms work. So it's just going to walk you through like what some of the code looks like, and you can also like mess around with some of the parameters by looking at the documentation. So for those of you that don't know Python, or don't have Python rather, don't know Python is a very beautiful language. I think it is chef's kiss. It is a beautiful language in my opinion, great for scientific computation, which is my main use case. There's some people do like app development, some people are doing like some web dev stuff. Streamlit, anybody heard of Streamlit? Streamlit is a way to like deploy web page type thingies for some of your projects. So that's an idea. You can also connect this with other tools as well. So the data sets that we're going to be using are going to be coming from this UCI machine learning repo. So UC Irvine in California has this website that has like a lot of actual data sets that you can actually play around with these machine learning techniques, okay? And so we're going to be using a few of them. Now, I reproduced some of the stuff from the slides here, okay, looking at this linear regression. And by the way, Jupyter Notebooks, very nice. You can run them cell by cell. Okay, you can run them cell by cell. So if I hit click play here to run that cell, it actually like does run the code in this block. And then it pauses, then you can like look at the code at the next block. And it also allows me to do like markdown. So this is how I get like the nice math stuff to show up here. So by the way, also learning LaTeX is another skill for writing technical documents. So we're gonna start with linear regression, a basic linear regression task. Again, I wanna fit a line to my data set. I talked through some of the math here. I won't really get into it here. So we're gonna look at this code here, okay? The main library that we're going to be using is scikit-learn. We import that as sklearn. Well, it's done with sklearn, and I'm going to mask that, alias that as sk for scikit. Ah, clever, right? Okay, so scikit-learn is going to be where we're going to get all of our algorithms, okay, for these like small-scale data sets. Okay, we can like even like scale it up as we please. Just got to be careful with that. So we're going to download the 2 of the data sets from the machine learning repo. This is the wine quality data set, basically looking at different chemical factors to see if we can like classify a wine by its color, red or white. Okay. Now, pandas is another amazing Python library, especially used for data analysis, looking at data frames and the like. We can always talk about that. Let's actually run this code and see what happens, because let's see what is done here. So we actually print some information about the data set. And that was not the block that ran. Okay. Is it running? Please run. I'm scared. It doesn't like my wget. Okay. This is why we have backups, kids. Okay, this is why we have backups. Yeah, let's just go to my Kaggle notebook here. Yeah, so sorry about all that, everyone. Tested it earlier, it seemed to work, but I guess things are funky. Okay. Okay, so run that just in case. Okay, all the math has rendered. Yeah, so Jupyter Notebooks, if you're in like a computer science class or maybe even a math class that does these kinds of things, very nice to do it step by step, and you can actually like write stuff out in plain English in those text cells and those markdown cells. Okay, here we go. Now I can actually run this. Okay, so what we're first going to do is get the data set, and then we're going to look at some information about it. Okay, so I'm going to print some information about the columns here. Okay, there's a column for fixed acidity, citric acid, sugar content, chloride, sulfates, its pH, density, all this stuff. Quality, that's another kind of target that we have. ABV, and then the color. Okay, sometimes whenever you explore a data set, just some data science tips here. Okay, just look at what your data set actually is. Like, look at the first few entries. Get your column names. If the column names aren't as explanatory as you'd like them to be, maybe there's a data dictionary or data guide out there somewhere that tells you what the column is, the name of the column, what it's actually measuring, and data types. Yeah, data types are pretty important. Bane of my existence sometimes. Fun fact, I learned that in Power BI, apparently if I want to like plot a line graph, it treats zeros as nulls and doesn't include it in calculations. That's bad. That's not fun. All right, so we look at our data set, we think about some things, and hey, we even get some information about the variable types. Are there missing values? Now, take a look at this thing. This is called a scatter plot matrix. We basically take a bunch of our variables, plot them against each other, and we make these scatter plots. Now, why am I talking about scatter plots? It's because I'm thinking about linear regression. I want to see like if I have data that kind of fits to a line, perhaps. So let's take a look here. Maybe fixed acidity against volatile acidity. Okay, it kind of looks like just like a little cloud. But maybe you can fit a line to that. Let's see, what's one that I really liked here? I think this one here, this sugar, and I'm trying to remember what it is. I think it's free sulfur dioxide in this one here. That guy looks like, kind of fits a linear relationship. So in your exploration of your data sets, depending on the thing that you're trying to do, here I want to do linear regression, I'm like, what two variables look like they may fit a linear relationship? And this is at its basic stage. It's at its basic stage. So we're going to go ahead and pick out, oh, and by the way, this is also the correlation matrix. You can also do that. It tells you like how strongly linearly correlated those two variables are. So of course, obviously in the diagonal side, yeah, every variable is strongly correlated with itself, correlation of 1. But you can see if we have a positive correlation in some of these cells, weak, very weak one here, decent here, or a negative correlation. Maybe they're negatively correlated. As one increases, the other decreases. Okay, just some basic data science things here. Explore your data set. So what we're going to do is we're going to look at density and fixed acidity. So we're going to go ahead and plot that here using matplotlib, one of my favorite libraries. That kind of looks like a line, right? I mean, you got some outliers, but most of the data is looks like it's concentrated around the line, right? And this is where the heart of the matter goes. Okay, we're going to go ahead and use the scikit-learn linear regression bit here. So in this cell, okay, the first line here, we're going to import the linear regression, I don't know what you call this in Python, a class, I suppose. Module, yes, yeah, module. The linear regression module from that bit there, scikit-learn.linear model. Okay, there are many different linear models, but we're going to use linear regression. And we're going to, this one here, especially when you do a lot of machine learning tasks, train, test, split, you want to be able to split up into your training data, like what you study for your flashcards, and then the test set is going to be like, well, you sit down for the actual test. That's a good analogy, right? All right, your training data, that's what you study, and then the test set is the actual exam. All right, so we do a bit of stuff here. I'm going to put some of this stuff into arrays, and I'm going to build a model here after I've done the train test split. Okay, this is a typical verbiage that you would see in a lot of these machine learning tasks for train test. I'm going to make a model object, and I'm going to fit the model. And then I'm going to say, okay, what are the coefficients? Okay, so I can see here, I have density is equal to that number times fixed acidity plus some intercepts number. So, hey, that's my y equals mx plus b kind of thing, right? Hey, we're back in algebra class, right? We know how to find equations of lines. And I'm going to go ahead and plot that. We have our training set in blue, our test set in red, and there's my regression line in orange or whatever bright color that is. What do you think? Did it do a good job? It captured most of it, right? Yeah. This is what you want to do. You look at your model, you fit, and then you assess. Many ways that you can assess it for linear regression. There's ways of doing that, like R-square, for example, or mean square error. Okay? We can kind of get an idea, like it does a very good job of predicting density from fixed acidity, just from our data set here. Okay, we can do that. That was one example of supervised, remember? Okay. But now we're going to do this, but now we're going to look at the color of wine. Okay, and in this cell, I'm going to plot the same data set, but except now I'm looking at it by the color of the wine. Reds are in red, and whites are in, well, not white, because then you wouldn't be able to see it. It's like that champagne-y, Chardonnay-ish color, okay, or a Sauvignon Blanc, if you prefer that a little, although they're got a bit more of a green tinge there. Okay, so we kind of, what do you see based on this graph? What general relationship do you see based on like the wine color and some of these features? Reds are more acidic. And if you know anything about like wine chemistry, okay, that kind of makes sense. Something about tannins or whatever. And of course, if you taste certain reds, like, yeah, you'll get like some of your more bitter ones, like, I think, what are they? Chiantis can be a bit on the acidic side. I'm not really a fan of that. But your whites, like your Sauvignon Blancs, your Chards, okay, they can be a bit on the sweeter side, not as acidic. And of course, it's not a perfect relationship, but it's just a general overall idea, right? It's just a general thing that we see. So now the question is, can I do a classification task? Okay, so we're going to do something called linear discriminant analysis here. I'll skip over really what it is, but we're basically fitting a line. We're finding a line to best separate the data. And here we are. That blue line there is my decision boundary. Things to the left of that line, those are classified as a white. Things to the right are classified as a red. How do you think it did? Pretty good, right? I mean, there is some misclassification to be expected along the decision boundary because that's like our fuzzy area, right? Some features may be shared. And these are just looking at two variables. You can probably look at other variables and like get this. Now, there's a better way of looking at this kind of thing called a confusion matrix, and I make one here. And a confusion matrix is basically what it sounds like. How confused is the model by classifying these things? 38% of the reds were correctly classified as red, whereas 96% of the whites were classified as whites. It didn't really do a good job with the reds, did it? No. So you don't just like put out a model and don't think about it. You gotta look at the metrics, okay? You can look at so-called specificity and sensitivity, type 1, type 2 errors, if you've heard of that in statistics. You wanna be able to make sure that it can like pick out correct features, especially for binary classification, because if you do this for like n-class classification, it's gonna get a little funky. Like, this is a train, buddy, that's a burger. Sir, this is a Wendy's. All right, so it's okay. So we can probably try a different one called the support vector machine. Again, kind of fitting this line type thing. And we import now linear SVC for support vector classifier. There's literature about that. It's a popular basic machine learning task. Okay. I had an issue like plotting the actual decision boundary, but I can still look at the confusion matrix. And wow, this one did worse with the reds, didn't it? 38% before, now it's 29%. But hey, 98% for the whites. The same data set. I did the same train test split. I didn't change anything about that. I gave it the same data set. Okay, it's like, you know, like for example, like in numerical analysis classes, okay, the assignment. Write your own finite element solver. That's the task I'm giving you all. Jonathan could write one. That works perfectly. You, sir, what's your name? Eric. Eric could write one. That also works perfectly. And you, sir, what's your name? Sergio. Sergio could write one. And maybe he accidentally divided by 0 somewhere. The same task for different people, but they thought about it differently. So whenever you choose your algorithms, okay, you want to make sure you have a use case for it, okay, if there's any sensitive things. Maybe this thing got tripped up by some of the outliers. Okay, that's another thing. Got tripped up by outliers. Okay. So we're going to, yeah, so bye online folks. Thank you for tuning in. We have to turn in the microphones.